We're going to bring on Mr. Pratik Shukla. He is my partner in crime in artificial intelligence. And when it comes to artificial intelligence, we have applications for crop circles and examining and studying artificial intelligence and how on earth can we decode these crop circles and make sense out of them and so forth. And this young gentleman is so brilliant. He makes me feel like I don't have any intelligence, So I mean, not even artificial intelligence. I got zero, right? Bright young gentleman. I'll send him a quick note, but I believe he's going to come on any second. And it's a very fabulous presentation that we have here. Is my good friend and buddy, Mr. Pratik Shukla. And for those of you that are saying, what in the heck is James Michael Alric, otherwise known as Jim, or, oh, I don't know, SpongeBob, but it sounds okay. That's Patrick Starfish. Deal with a smart, brilliant gentleman like this. Well, the answer is I met this gentleman at a artificial intelligence and machine conference known as AIM 2024. The poor guy was sweating so bad in the sun, and I offered him Pratik, out of the goodness and bottom of my heart, offered you the shade, and I took the heat for you, my friend. And and this guy's a gentleman because the whole time I had this beautiful, brand new suit on. The whole time he didn't bat an eyelash. He didn't tell me that I had chocolate cake frosting all over the sleeve of my suit, and total gentleman about it. Is to this day I thank you for not exposing me for that. One thing, Pratik, when I was presenting and I was talking about my AI computer hardware and software, did I have chocolate frosting on my sleeve then, or was it afterwards?
I think it was afterwards. Yeah.
All right. Well, it didn't show up in the proceedings anyway. So yeah. All right. So that's a good thing. So I'll let you present. And folks, just so you know, my contribution to this particular presentation, you saw my field investigator presentation earlier, and so that contribution was just saying, okay, Snapchat AI versus other types of like Google image search, etc., and what we could do with crop circles and so forth. So at least I did that. This presentation is completely 100% Pratik Shukla's own work. And then what I did was I took some of the verbiage and I simplified it for mere mortals such as I, since I have somewhat of an artificial intelligence background, not as in-depth as Mr. Pratik. And then if you see anything that looks kind of silly, that was me too. So we hope to keep your attention. All right, go right ahead.
All right. Can you all see my screen?
Yes.
All right.
Yeah, let's see. Okay, got it.
All right. Good evening. Thank you so much for a very warm introduction, Jim. And my name is Pratik Shukla, and I'm from UMBC. I'm a PhD student here. And today's talk is on AI, on crop circle phenomena, and it's more about the methods and roadmap that we have built so far. And this is a result-free preview of how we're going to study circular fills patterns with AI, and I'll briefly cover the motivation, define some clear inputs and outputs, and then we'll probably walk through the pipeline and what kind of models we can use for segmentation or for finding out some fine structure. And our goal here is simple. We want to recognize what we are seeing, and we want to characterize it. So, like symmetry, order, the ring counts, the confidence, and while we are staying neutral and hypothesis-driven and transparent about the uncertainties. Right.
Yeah. So when you see something kind of silly, that's my cue. I put it myself. So I did want to remind you folks watching that all works are copyrights of their respective owners, but non-human intelligence made crop circles are copyrights of the aliens who made them. And so these two aliens here, I don't know if they're from Zeta Reticula or whatever, but they don't understand every time they charge their UFO why it creates a crop circle. So, all right, Pratik.
All right. Okay, so let me start with why this is interesting. And when people say crop circles, they often this mean one thing, but on the ground we actually see at least three different phenomena. So first is irrigation. There's a central pivotal system that leave near perfect circles. Second one is geologic landforms like natural features like fly pans, and the third one is intricate formations like high symmetry, crisp edges, patterns reported in fields. So it's the same word but very different origins and textures. So because of the variety, scientists and field investigator they need tools that do two things for us: recognize what we are looking at and then characterize it in a standardized way. So think of it as moving from that looks unusual to here is the symmetry order, ring spacing, and all the statistics and all the details about it. So the question is why? Why does it matter? So there are a lot of benefits. One is agricultural, or understanding the nature, studying anomalies. So for reports that don't fit irrigation or geology, consistent geometric fingerprint that lets us separate rare but natural edge cases from puzzling events, and also possible non-human intelligence that we want to figure out. And if we want the conversation to be productive, we need objective descriptors or open methods that we can all share. And okay, so when I say AI, I mean two concrete jobs. First, recognize or characterize, and then what we're looking at is education or geological landforms or intricate formations. The second one is to characterize it. So actually measure the geometry, the order, and everything. And just as important is how the algorithm behaves. It must be neutral, so it does not give higher weightage to some class and lower weightage to some other. So it has to be hypothesis driven, and we state in advance what features we will taste and what outcomes we can confirm or disconfirm as an idea. Um, yeah. Okay. Jim,
Okay. All right, for you UFO dudes and dudettes out there, and you UFO chick that belongs to retired Staff Sergeant Gene Sticko. Yeah. All right, so here we go. And for you, Mr. Eric Hartwig, MUFA, Massachusetts State Director. All right, you ready? Mark, set, go. What's a computer software requirement? Okay, so for software engineers out there, and I got lectured once by a very close friend of mine, Chucky. If you're watching, hi, you know who you are. Computer software requirement. He lectured me, and he epistled actually like 40 of us in an engineering conference one day. This was like about 9 years ago, and he said, "Jim, a computer software requirement has one input, one process, and one output. So and that's it." And there was like this huge to do about it, and all these software engineer geeks and stuff. Pratik, you're gonna have to deal with this if you go to industry. Stay in academia. So, so as an example of an input, a UFO comes over and it's doing some weird stuff to the grass, and then a process. Farmer Brown gets quite angry because he's processing what's going on. The output, oh my God, look what happened to the poor guy's crops. All right, Pratik.
Yeah.
And now, computer software requirement may be allowed as an array, which basically means the same thing, but in multiples, such that there's similarities. For example, if you have anomaly number 1, which is a regular UFO, and then you have anomaly number 2, which is an orb type of anomaly, and the process may be different. In the second case, it's an array. Instead of Farmer Brown, you got Farmer Groundhog, and he's really mad because look what happened to his crop. All right, Pratik.
All right. Okay, so let me define the requirements so we all know what the system will and won't be able to do. So for the inputs, we start with images. Let's say aerial images, satellite images, or ground photos of circular formations. And when available, we will also add some optional context like recent weather and wind, or crop type or yield data, and some time-aligned field reports. And those context signals aren't required, but they help in some ambiguous cases. Now, the process is the pipeline standardizes the image and extract edges and texture and unwraps the polar coordinates and computes the radical and other features. And a learning model like a CNN, or let's say a more advanced model like a vision transformer with a small geometry head, and we'll use those features to both sort and measure, and then we'll calibrate its confidence against a holdout set. So we'll live out a specific set of examples just to taste our model on. So the output will be, let's say, first a label. So whether it's an irrigation part or geological or very intricate kind of design. And the second is the geometry, the symmetry order, let's say, or ring count or radial profile that shows how intense, intensity changes from center to outwards. And finally, we will report the confidence and calibration on our left out taste data. Okay, so the data plan is, let's say we're starting with imagery, and we will pull from public satellite tiles and credited web photos, and we'll keep the classes balanced. So we'll have, let's say, roughly 100 images of each class. The metadata for each image will record the date, maybe the approximate location and when, or maybe the camera angle and even the resolution of the image. And this field let us study how viewpoint quality affects performance and prevent accidental leakage across splits. And for other contexts, we can also use some reanalysis weather data, like for temperature or wind or maybe precipitation if needed. For labeling, we're going to use some conservative labels and seek consensus review and explicitly allow an uncertain tag. So when people are not certain what kind of image is it, they can just don't classify it in one of the other ones, and that prevents forcing ambiguous cases into the wrong bucket, and gives us a clean subset of high confidence evaluation. Okay. So this is kind of a visual taxonomy. The graph on the left extreme is irrigation. The middle one is geological, and the one on the right is, let's say, we are saying that it's a more kind of intricate kind of graph. Okay, so some baseline models. We want to compare our like we'll create some baseline models to evaluate our data set on. So let's say we can start with some basic machine learning algorithms like random forest and maybe support vector machine SVMs, and then we can also benchmark it against some deep learning based models like ResNet or Vision Transformers. Vision Transformer is a little bit advanced, and since it's based on transformer, it requires a lot more images. But we can definitely start with ResNets, and we'll also attach a geometry head to predict n or the ring counts alongside each classes, and we can test multimodal fusions to blend images within the context of, let's say, some weather data.
Pratik,
Mhm.
if I understand correctly, you said geometry head. So that's like that guy with the googly eyes, similar to the band Radiohead, right?
Yeah.
That's what you're talking about.
Hmm. Yeah.
All right, cool. Thanks, man.
Mhm. All right. So for training and evaluation, so I'm not gonna go into details, but let's say once we have trained the model, how we are going to evaluate it, like how it performed on some unseen data. So for we may use some standard machine learning evaluation metrics like F1 or accuracy, or maybe a mean absolute error for statistical data. And we just want to keep our model robust. We don't want to taste on the trained data, or we don't want to tell the model before and what we're going to taste on. So we're going to keep the taste data separate. Um, So some of the planned experiments is we're going to start with, let's say, some image only baselines. So CNN or Vision Transformer can learn. So how they basically learn is, let's say we have a bigger image. It divides an entire image into small patches, and then it learns different features, and they correlate it with different parts of the same image. And maybe in experiment two, we will add a geometry head to better predict or better estimate the N or the ring estimates. Then maybe in third experiment, we'll try adding context to see whether it's helping or not. Um, on the fourth one, we might try cross-region transfer or low-resolution trial, or maybe some oblique photos to see how it's doing on that kind of data. Yeah. So
Thanks for clearing your throat there, dude. So, all right, ethics. All right, we have a highly, very ethical artificial intelligence computer program. It's very ethical, and the work is going to be ethical too. As Pratik scolded me and scolded me. Said, Jim, we have to be ethical. We must credit the photographers in this work. So, like the crop circles, we didn't invent them, and we didn't take those pictures. Who owns the data that we're using, or the metadata and so forth that we're using to train this artificial intelligence? Respect land privacy. And if you don't, be like me and fly your drone over their fence and take all the pictures you want. But other than that, you should respect their privacy. Don't overclaim, Mr. Pratik says. Like I like to brag, don't do that. Quantify uncertainty and explain the limits of your artificial intelligence. So if that was my AI right there, that jalopy from, I don't know, looks like 1952 Pratik or something. I'm telling you guys that 1952 car can go 3.5 times the speed of light. Now that's obviously an overstatement and an overclaim, and Pratik is saying, don't do that. I'll let you take the final line, and I'll be quiet now.
Okay, so we'll sell the pipeline for like same model, but we'll have different data sets for evaluation and training. For risk and mitigation, first week, or we'll try to sort out weak or maybe biased labels, and every other labels can be noisy or reflect our own expectations. So we will use the consensus review and allow an uncertain tag rather than forcing a guess. And then we'll run a sensitivity analysis, retaining it with and without some borderline examples, maybe to see how much labels sway the results. Second, we are going to mix the image quality, and photos come at different resolutions, different angles, or maybe different compressed levels. So we'll train with robust augmentations, like we'll do some rotations, some perspective jitters, some blur or jumping artifacts, and then we'll do a condition-wise reporting. So the performance is broken out by resolution, viewpoint, or lighting instead of hiding behind a single average. Um, Third one is the context aligned errors. So weather or yield data may not line up perfectly with the images, image time and place. So we'll use a windowed matching, a tight but explicit time space window, and run ablation study with and without this context. So we can generalize in which cases this contextual data is helping us, and where it's not helping or it's making poor predictions. So what success looks like? So first, a reliable separation of the three categories: irrigation, geologic, and intricate formations across region and dates. Not just a good average, but a stable performance where we move in time and space. Second one is interpretable geometry outputs, let's say symmetry order and ring counts, the radial profiles with tight error bars. The numbers should be precise enough that the two different teams would reach the same conclusions without any uncertainty. So, and the third one is honest failure modes. Well, so where the model struggles, like maybe low resolution or oblique angles or maybe lookalike textures, and we'll quantify the measurable gains from textures like weather, crop data or reports when it actually helps. Okay, so here's how you can collaborate with us. So first, image permission and geotags. If you own photos or have access to fill imagery, we would love to get permission to use them with proper credit, of course. And any geographic coordinates or captured details you can share. That metadata is gold for fair evaluation. Um, Second is help us build an open benchmark so that other people can use it in the research study when they're trying to maybe build some model or do some analysis. So we can have the same benchmark so then we can share the results and compare. Third, we welcome constructive critics, challenges and challenge our assumptions, poke our splits, question our metrics, and those critics harden the methods and evaluation so results stand up outside our lab. So now the question is, why do we need this deep models? So handcrafted geometry is strong, but real images aren't laboratory perfect. They vary in angle, lighting, and resolution. Some of the edges they get fuzzy, rings deform, and perspective can hide the very patterns we want to measure. So that's where CNNs or vision transformers help. They learn invariance to rotation and viewpoints, and they pick up subtle textures like lodging patterns or streamlines that simple feature extractors may miss. So our hybrid plan is pretty straightforward. Let geometry give us interpretable measures, and let deep learning models or other deep models give us robustness to messy imagery and bring in the context. Like we can give it other context like weather or crop data and other reports as a different channel other than the images. And when it disambiguates lookalikes. Um, some CNN does baselines. We'll start with basic CNNs. So it take those patches and compares. It will share the weight across the image. So we'll have a it is easier to generate inferences when we start with CNN, and it's a really strong baseline. And we can try different architectures like ResNet or ConNet Tiny One if we don't have enough resources available to train the model on. And we can use three heads as discussed before. And for tasks, we can use CE and L1. So something specific to the statistics, and some loss function like CE specific to the images. Okay, so the data pipeline and augmentation. So before we start training, we pre-process every image in some way. Let's say center crop or resize to a common size. Let's say 256 by 256, and normalize the pixel values. So that really actually helps the model to learn fast and actually converge, so we can have a good result or a good output. Then we augment to mimic real level messiness like full 0 to 360 degree rotations, horizontal and vertical flips, maybe a bit of perspective warp, twerks to brightness and contrast, and even some JPEG artifacts. This forces the model to learn the pattern, not the photography. One small but important tip is whenever we rotate or reframe an image, we store the original orientation if it's known. Later, that that can become a feature. For example, um, to taste whether certain formations tend to align the wind direction or maybe filled rows. So once we have a stronger CNN baseline, we'll move on to a vision transformer. Vision transformer are used pretty much in all of the academic projects which are focused on images at the moment. And we'll start with Vision Transformer Tiny or Small using the patch size of 16. I'm not going to go too much into the details of how a Vision Transformer works, but it's a pretty powerful model just for images. Okay, some segmentation for fine structure. So it teaches the model to outline where the structure is, not just what it is. So the task is to segment ring bands, large area, or pivot hardware. That pixel level map gives us a clean blueprint of the formation. And for labels, we can start chip with, let's say, a wear mask, detect edges and fit circles to propose bands, and then tidy them up. And if we have time, we add a small hand label set, even maybe, let's say, 30, 50 carefully annotated images that can go a long way with unit. So unit is an architecture which is based purely on CNN, but as we reduce the resolution, we lose some important features. So to avoid doing that, we use unit, which is a powerful version of CNN. It's made out of CNN and bunch of skip connections. Okay.
Oh, here's my cue. Okay, so Mr. Pratik is now talking about multimodal fusion. Well, multimodal fusion for idiots like me. So if you look at Pinky and the Brain, that's Pratik on the right, and that's me on the left. Okay, it's trying to explain to me multimodal fusion for idiots. So fusion means integrating data, computer data, information from several so-called modes. In other words, if you have images, pictures, text, etc., and you're going to combine pictures with contextual data, descriptions in text, metadata, dates, geographic locations, or annotations. And so why do this multimodal fusion for idiots? Well, what it does is it improves so-called decision making, or in other words, it improves the artificial intelligence which makes decisions.
Okay, so
And this is multimodal fusion for a software engineer like Pratik. All right.
okay, so we'll here try two simple strategies. So first, we'll start with early fusion. We'll take an image and using image embedding and concrete a small context vector. Let's say other it could be weather, wind data, precipitation data, some other data like that. And so the model reasons over pixels and context together. Second, what we do is we do late fusion. So we run an image only head and then context only head, and then stack or maybe average the logics and make a final decision based on those two separate outputs. So this keeps the each stream honest and lets us evaluate the contributions. Because context won't always be available, we train with context dropout. It's around zero point 0.3, so it does not only learn from contextual data like weather data. So it means that during the training time, we randomly hide context in, let's say, 30% of the examples, and forcing the model to stand on its own when metadata is missing. So the result is a system that benefits from context when it exists and still performs reliably when it's not available. Okay, and the self-supervised pre-training. So labels are scarce, and we'll start with contrastive pre-training. So on a pool of unlabeled images. The idea is very simple. We teach the network that two heavily augmented views of the same photo should land close together in an embedding space, and views from different photos should land far apart. So that builds a feature extractor that already understands the circle, edges, and textures before we even show it a class level. So we do not actually need label data. It can generate labels on its own, and then we can maybe verify it with what we have now. Um, then we fine tune our on a small labeled set, let's say 50 to 200 images, and we typically get performance that's surprisingly strong and robust to rotations and perspective. The key here is how we make the positive pairs. We apply heavy rotations, let's say full 0 to 360-degree rotation and viewpoint jitter, a bit of perspective warp or maybe blur, so that the model, learns invariance we care about. And after pre-training, the classifier head only has to draw boundaries in a clean, rotation-aware space. So it avoids overfitting or it reduces overfitting, and which is better for real world reliability. Okay, now the model risk and mitigation. So we already discussed how we are going to avoid overfitting. If the model memorizes the training image, it won't generalize. So we'll use a smaller backbone first, apply heavy augmentations, and add maybe an early stopping on a geography-aware validation split. So we quit training the moment validation error turns up. So our model won't um, just overfit on the training set, and it will be able to generalize on the data it has not seen already. The second one is data leakage via near duplicates. So two versions of the same photo, it's different crops or compressions, can sneak into taste and train data. So we'll run a perceptual has deduplication before we split the data. So anything that's visually the same lives in only one partition. The other one is class bias. Let's say if irrigation images dominate, the model tends to predict irrigation too often. So we'll use balance sampling during training and when needed, focal loss to upweight the rarer case, so mistakes there matter more. So let's say we have very few example of a single class. We will in the loss function we will force it to way higher, so it learns to better predict those kind of classes. Then we'll do angle and scale shift. Circle arrive at different zoom levels and viewpoints. So we'll do a multi-scale evaluation and probably taste time augmentation with rotations. So predictions are stable when we resize or rotate the inputs. Okay, on compute time, it's very feasible. We can run it on our own laptop with or without a GPU. If it's just a CPU based machine, then it might take a longer time. But let's say if even if you have let's say we use ResNet 18 and we train it on about 2,000 to 3,000 images at, let's say each image is 224 by 224 pixels, it will take around 30 to 60 minutes on a single GPU. Let's say maybe V100 or A100. Um, but for vision transformer, it's a little bit heavy on the computation time. It will take around 2 to 3 times longer than resonant based architecture. For the small unit segmentation, if we run it for 50 labeled masks, it's very quick, like 20 to 30 minutes. And if we had self-supervised pre-training on a small unlabeled pool, expect maybe around 2 to 4 hours of training time. But this step is optional, and it usually buys robustness to rotation and viewpoints. And yeah, that's about it. Over to you, Jim.
That's so, Pratik. Thank you so much. Is excellent preliminary work and planning. So I put a lightning bolt next to the first result because to me, my understanding is that ResNet 18 is, correct me if I'm wrong, it's similar to or related to convolutional neural networks, which I was asking you about when I met you last year at the AIM conference.
Yeah, that's right. It's a combination of convolutional neural networks.
Okay, and so 2,000 to 3,000 crop circle images. It only takes half an hour to an hour on one consumer GPU, like an NVIDIA or whatever. So what you're telling me, computation power estimate. You have an NVIDIA GPU, which you could get that like on a plug-in card, right?
Yeah, that's right.
A plug-in card, NVIDIA graphics processing unit, which a lot of people know that are into computers know that, and you get 2,000 or 3,000 crop circle pictures, and so this, your model and your architectural model for the neural network, artificial intelligence, it only takes 30 to 60 minutes to learn 2,000 to 3,000 crop circle images. That's it. In an hour, it learns all those, and then it'll be able to tell you when you give it an image, it'll inference, which means pow, in a second, it'll tell you what it thinks about that image. Did I get that right?
Yep, that's right. Absolutely right.
Okay. And VIT small, my understanding is, well, actually, you can explain to me what VIT small is, but my understanding is the advantage of VIT small, it's a different type of artificial intelligence model. And the advantage of that one is that it actually exceeds conventional convolutional neural networks when you get to, when you start getting deep layer neural networks. And so you put 2 to 3 times longer, I believe you meant 2 to 3 times the
Longer
amount
training
of
time.
images. Of images?
No, training time. Let's say if
2 to 3 times long.
60
Okay.
minutes, it will take, yeah, maybe 2 hours or 3 hours.
Okay. But then you have something UNet seg 20 to 30 minutes.
Right. Yep.
So
So
for the
Vision Transformer is something that's based on, like, if you guys are familiar with ChatGPT or any large language model, they're all based on a model called transformers. So Vision Transformer is as a model, it's the same model, but it's made specifically to process image data rather than text data. Yeah. And if you
okay.
take the original Vision Transformer, it has a lot of, maybe billions of parameters, but the small one is, we can start training on it. And if we get good results, we can move to the bigger one. It has billions of parameters, so it might take a little bit longer to train on.
Okay, so is it safe to say, Pratik, that VIT small, VIT meaning visual transformer, artificial intelligence, it takes, instead of 30 to 60, it could take 60 to 180, which that's not too bad, 3 hours, if I get that right. But on the other hand, you can train it with much more complex data sets, and
Exactly.
that's what the advantage is.
Yep, that's right.
Yeah. So in 3 hours, which that's not too long. And what kind of how many consumer say GPUs, NVIDIA or HI Radeon processors in doing that, or is that different?
Let's say just one NVIDIA, let's say 100, but it's totally fine. For one, it's work. Let's say if we don't have GPU and if you want to work it on a CPU, it might take around 6 to 7 hours, but it's still possible to train it on a CPU.
Okay. And if I understand, Pratik, the end result. So that's the learning phase. The end result, the inferencing, is similar to a filter. You've got the end result. You put an image through, and you could do something similar to, correct me if I'm wrong, you could say it'll categorize it, and it might come out saying human generated crop circle or anomalous crop circle. Did I get that right?
Yep, that's right.
Okay, beautiful. Yeah, excellent work. And last but not least, we're talking about benefits of artificial intelligence for crop circles. I do truly think that you're onto something, my good friend. I don't know how many scientists and engineers are doing this, but benefits study, was it anomalous and non-human intelligence generated, or is it something related to, I'm not sure if they said like micro patterns or micro bursts. You get these bizarre patterns in the grass or in the crops. Is it safe to say you could also use it to study the success or failure rate of different conventional irrigational crop circles? And so if you look on Google Earth, for example, you could survey the whole thing, get your training data sets, and at the end result, you could say, well, we know by certain irrigation, certain tram tracks, and things like that, certain patterns in certain regions of the planet, there's a higher success rate of crop circles, and the end result, you could help feed the whole country and give us more loaves of bread to eat. Is that what you're saying?
Yeah, that's right. Yep.
Okay.
So
Totally.
once we have a model, we can train it on however many images we want. So the longer the data set or the more detailed the data set, the better it is for the model to learn. So yeah, that would definitely help.
Yeah, this is. Have you shown this to Professor Milt at all? Did you bounce it off him just to say what he said?
No,
Or
not
you're afraid of the NHI UFO stigma? So you're like, oh,
I'm going to show it to him maybe when he comes in on Tuesday. Yeah.
Okay. Yeah, well, if he doesn't like it, blame it on Jimmy. Say it's Jimmy's fault. I met him at the AIM conference, and they were carrying him away in a straitjacket, and he's like, "No crop circles." But that is unfortunate with the UFO and crop circle community. There is a stigma, but I can tell you there are brilliant people such as you. I don't know if you heard of Dr. Avi Loeb. He was presenting earlier. Very, very well known. He's talking about he is talking about 3i Atlas, that huge super duper thing in our solar system. And we have the Tedesco brothers on. We have Dr. Rudy Shield, who's about ready to enter our Talking Points roundtable. Brilliant scientists from the likes of you. You're going to Maryland, Baltimore County, which you may as well be going to MIT. Shame on you. Now I can't hang out with you. I got to go visit you out in Maryland. But so, wonderful, wonderful school, and you've got brilliant folks like you, and they're all saying there's something to this non-human intelligence or the crop circles. We need to look into it, and appreciate the demo and the way you showed it could be done with a simple graphics card input, and the end result is understand nature, understand anomalies, and more loaves of bread could be the benefits. Appreciate it, Pratik. So, my good friend, you are wholeheartedly welcome to stay online in our back room for our 6 p.m. roundtable if you have time and if you like. If not, we understand. But either way, you're welcome. And I do thank you, my friend, very much. And I'll always treasure and cherish talking to you for the last couple of nights, saying 5 more minutes, Pratik, 5 more minutes, and it was like, I think it was like 4 a.m. when I was going to bed. I'm like, 2 more minutes, and I fell asleep.
Yeah.
Okay.
All right.
Well, thanks again, and I'll speak with you soon.
Yep. Thank you.